Welcome everybody to the third week and the last week of lectures of the course Intelligent Systems. We are going to start now with the theme of machine learning. And we'd also have half a lecture on ethical questions and half a lecture on philosophical questions on Wednesday and Thursday. On Wednesday, one of my colleagues will take over the lectures, Peter Bloom, who is actually an expert on deep learning, and he'll luckily give the presentation about deep learning. I will lecture today and tomorrow about principles, introduction to machine learning, principles of machine learning, some ideas about machine learning, so that you have the basic foundations heard for the first time. Of course, this is a very general AI course, so you won't get into the details. But luckily next year, in the third year of the study, there is a course fully devoted to machine learning, and you will see a lot of detailed work there. What I'm going to do today is to talk, first give a sort of general introduction. And then guide you through sort of the machine learning methodology in general with some examples. Also how it is related to the agent work that we did in the first week and the search paradigm, but that will come more explicitly tomorrow. I then really sort of practically hands-on try to explain you a very simple machine learning method, and that's Bayesian classification. Or naive Bayes, as it's usually called. And then I want to talk about ML for the project. So how is machine learning used in the AlphaGo? And how can we sort of use some of the ideas also in our Schnapsen example? For personal reasons, I would appreciate if we could have a shorter break today. So if we'd say we have a 5 minutes nature break and then finish 10 minutes early, if that would be okay with you. Yeah? So I want to start with introducing you to the topic of machine learning, and this is more or less something that was 5 years ago or 10 years ago, still something that sort of was really necessary. But nowadays, it's very difficult to open a newspaper without machine learning, which nowadays has almost been synonymous with AI being on the front page. And still, I want to give you a more systematic introduction, talk about several different types of problems and so forth. And that's what we're going to do in the first half of today. So, as I said, it's very difficult nowadays to not come across machine learning in the newspapers, and of course even more in the scientific literature. And that goes from applications in image recognition to almost artwork, where you apply machine learning models also in a generative way to the research that is done with the interaction of robots and humans, which is very often machine learning based. And of course also the sort of negative implications, the problems that an approach to intelligence might get you into when you learn it on existing data. Because sometimes the models are wrong, but sometimes also the data itself is biased in a way. And what you learn from a biased data set is often something very biased, as we've all, I think, heard and learned in the rather sort of racistly biased search results that were given at some time by the Google search engine, which was really a problem of bias in data applied to the learning algorithms in Google. We're getting into that on Wednesday, discussing a little bit more. Not that there are any solutions, obviously, to these kind of problems, but at least I think we as computer scientists, AI as information scientists, really should be thinking about these topics very carefully because they are related to our everyday work that we do. And that might be a little bit less to what you're doing now, but I think already in your bachelor and later master thesis, I'm sure that most of you really will do some work that has, in one way or the other, a relation to ethical questions and philosophical questions. And now we want to focus on the kind of intelligence that we can achieve by machine learning or learning. And it's obviously one of the oldest notions in AI that machines need to adapt in order to be called really intelligent. So you want your machine to perform better over time, given the same measuring sensoric information, and learn from its mistakes. So if a machine really does stupidly the same mistake again and again and again, you wouldn't consider it very intelligent, would you? So we really need some mechanisms so that the mistakes from the past improve our performance in the future. It is very difficult, though, to apply these these learnings or this technology in the first place really in life environments. So if you really want to have your robot automatically learn how to deal in an environment, you need to train it. And it's very difficult to train it really on the right data. So if I have a company and I say, okay, I sell you this robot, it's very intelligent if you train it for about a month. Then few people will actually buy it, I would guess. So, but it needs to be trained on each of the new environments. So what is often done is to separate the real action learning problem, the development of these learning algorithms, and the development of the agents. So we now develop methods for machine learning, and later it might be applied to these physical agents. And in the beginning, you would do a lot of simulation and try to model to learn your models on these simulations before you actually really apply it in this agent paradigm. But of course, the learning is omnipresent in these kind of really intelligent agents. So you have to learn. You can learn properties of the world. You can learn properties of the expected results that you can achieve. You can learn the expected outcome of your action. If you translate that to the Schnapsen, we can learn what the best result would be if we play a certain card in a specific state of the game. So we can even learn the goals, that we adapt our strategies to specific goals, and the goals become more specific and better according to the game that we play. And then the learning element or the learning agent itself has to be designed according to what kind of feedback it gets. It gets the standard sensing and so forth, but it might also get feedback from the user who says, okay, it's not clean today, try to do it better next time. And then we need to design an agent that can take this kind of feedback loop into account. In many cases, we are not dealing, as I said, with the agent in some kind of environment directly, but try to build our learned models offline. And in principle, all the things that we do in this course are also algorithms that are based on some data that we've collected, on which we do perform some offline learning and then do some prediction on the basis of this historic data using some machine learning models. Of course, this can later, or the ambition is to apply this later in some online agents who make their decisions on the fly. And in our Schnapsen game, we will actually do that. We will learn offline and then apply the learned results to our card game playing agent. So this is a typical example that I think you know from everyday's practice. The idea that you learn from your own behavior what is the chance that you would like to watch, which is the video that you would like to watch tomorrow, And this recommendation is given on the basis of your previous watching behavior. And this is a typical task of machine learning. In an offline setting, we collect what kind of watching experience you have. This is our data. Based on this data, we can make a prediction for the next video that we believe might be interesting for you. And that's the business model of many of the Amazons and the Netflixes of this world. We'll look a little bit more into the Netflix, but the idea is, I think, very clear. As I said, the idea is that you get some kind of input that you collect, and you make a prediction. That's a classification or regression that we'll look into in a minute. And the idea is that the learning algorithm will somehow adapt on the basis of some kind of feedback. So if it did the right thing, then it will try to stay, not change much. But if it gave the wrong answer or did the wrong decision, then it will adapt its algorithm in order to perform better in the next time. And that's sort of the basics of the idea of neural network learning. It's obviously now the standard state of the art, that you have some information that comes into the neural network, and you have some outcome, and according to the performance of the network, the internal working of this network is adapted, and hopefully then improves over time into a better performance of the entire network. And this depends so on the different kinds of feedback that you can get. You can have the fully supervised learning where you have a correct answer for each of the examples. So you're told exactly if something is right or wrong. If you would translate that to some kind of offline learning, then you have some features, some properties of your instances, and you have a classification whether it belongs to a certain class or whether it is a positive example or a negative example for a certain class that you want to classify later. So the distinction between positive and negative examples that are given up front is what makes these supervised learning algorithms. And the opposite of it is if you haven't gotten any information, so that's called the unsupervised, if you don't know up front whether your training examples belong to a certain class or not, but that you need to learn these classes in the first instance without any input from a human expert or from some experience. And then there are sort of approaches in the middle. You have semi-supervised learning, where you, for example, after some actions, you get some information, and you use this information in order to help you ask the next question, in order to find the right question, to maximize the gain of information, for example, in the classification process. And then there is a more offline-oriented learning method that we are not going to look into in this course. That's reinforcement learning, where you basically perform in some environment, and then you're given rewards when you're doing good in the environment and not, and you try to adapt to interpret those rewards in order to improve your performance as an agent. So it's just to give you some idea that when we talk about machine learning, we're not talking about a single well-defined task, but a family of similar things, and they are all related, but there are also very many different approaches to each of those problems. So look at some of the typical problems and the typical types of problems that have been addressed using machine learning. That's handwriting, car riding, or games. The games we're looking into at the very end. So here are 5 typical tasks of machine learning. Probably you're familiar with them, but I just want to introduce them anyway. The first one is classification. So we have some data and some discrete classes. And this is sort of the typical example, a typical example for that. It's one of the big challenges of early neural network learning, I would say. It's a data set consisting of thousands of samples of handwriting. And basically each of those little things is a letter, corresponds to a letter, which is classified to a number and a letter. And the task is to have I think each of the handwritten letters is represented as a 9x9 square. And given this input, the task is to classify the intended digit or character. And so you get as an input the handwritten digit, and as output you have to give it an ASCII code or whatever it comes with. And has been this huge training set with many variants of handwritten letters. And this has been one of the early training sets that have been people working on. And basically this problem is nowadays solved. So the top state-of-the-art systems now classify these new handwritten letters with a probability of less than a percent of a mistake. So it really is, they're really very good nowadays. I'm not leaving, but there are people driving around with a car, so it's a bit disturbing. Another version of the same problem that you're all familiar with and that you're all using every day is the spam filtering. So we all get far too many emails, particularly those that we do not want to get. And it's very good that we have an automated system that takes out, or at least classifies all the spam as being such. I don't know whether you have the same experience with the VU spam filter, who was, in my view, relatively aggressive and always filters out many of the nice emails that I get. Many student emails never get to me because of this spam filter. So this is, I would say, far less than a solved problem, but it's exactly the same. So we have input is some text, maybe some structured text in headers and what you like, but particularly it's the words and vectors of words, and the output is just whether it is a spam or it's not spam. Then we have a similar thing. We can say we now don't try to only recognize letters and spam or not spam, these kind of classes, but now we want to recognize images. So we have a finite set of faces, and whenever someone comes in, we want to recognize whether that's the same person. So we want to match some kind of data, which is usually represented as a higher dimensional array than the 9x9 representation of the letters, but still some kind of pixel array, and we just want to map that to a certain person. And again, the same as we need some training set, many photos of the same person, so that the classifier can be trained in order to recognize the main features that determine the distinction between you and you, for example. And even in problems such as weather prediction, we have similar ideas, or we can apply similar, we can phrase this as a similar problem. And that is it going to be, according to the definition that I have now, is it going to rain tomorrow, or is it a sunny day? And many of these weather sites, they have a finite set of representations for weather tomorrow, for the future weather, and that is going to be snowy and sunny and so forth. And then you just take as much information and as many features about today's weather, and you integrate them into some kind of predictive model that tells you it will be this day or it will be this kind of day. And of course, weather prediction nowadays, I think, has far more complex approaches to modeling, and they want to have directly the number of rain somewhere and then come out with this image, but it basically is based on the same kind of problem that you want to address: a set of feature data and some prediction into a finite number of classes. Yeah?
Isn't it based on simulations?
I guess it would, but what would the simulation be then?
Wondering how does that affect the classification? Because by simulation you already have the data and then you
Yeah, so the question is what the outcome of your simulation would be. So if the outcome of your simulation is a more complex prediction, then it wouldn't fall maybe under the category of classification. But you can phrase it as a classification problem if you want. But the simulation just means that you sort of forward apply a model that you have somewhere learned. And in this sense, it falls into this category. And obviously, the next example, the next slides will show that most of the things you do with weather prediction are not really simple classification, but other things. But it is good to think in these simple categories, because when you go out shopping for machine learning tools, then they are usually organized in these kind of problem definitions. So here's one that goes back more than 20 years, self-driving car-like. And basically what they did, they had a camera with 30 by 32 pixels that gave some representation of the road. And in total, each of the features could only be on or off, or I think it was gray, or I don't know whether they had different scales. Here they have different scales. So for each of those features, they had a scale between 0 and 1. And they had 960 of those features. And then based on those features, the question was, should I drive right or should I drive left? And should I drive straight on? In the real system, they had a little bit more than these three classes to make it a bit more smooth, the movement. But basically, they formulated the idea of a self-driving car already in 1995. And they drove from the east to the west, or the other way around, I don't know. The way they drove the car actually was by giving commands to a human driver. So they sort of simulated the automated car through an intermediate driver. So it wasn't directly implemented in the hardware of the car, but there was a driver who was told to do left or left 30 degrees or whatever. And that was the first self-driving car, at least in the decision procedures that were underlying this car. And this was based on learning of predicting if you have a white line. And of course, the models don't do that explicitly necessarily. But the idea is then that if you recognize that there is a sort of straight line, you just stay on a straight line, that would be then the best move. But I don't know many of the details, so I don't know how many negative examples they also had in their training set of misclassification, or in any case, this is they had only those three classes and showed the right decision to drive according to some driver, I guess. So, as you rightly pointed out, the classification of weather data into some discrete classes isn't really what you do in practice. So I think it's far more. And for example, regression or variance of regression is one of the more standard ones that you would apply in order to predict several values or a function that you could apply to simulate for the future. And regression basically is to predict a numeric value according to some function that is you try to learn from a set of data. So on the stock market, you have a lot of features as input, and you would love to, of course, predict correctly the value of the stock market of a certain stock in the future. So it's not necessarily that you want to know whether it crashes or increases, but you really would love to have the values so that you can actually maximize the possible gain. Unfortunately, this turns out to be, again, a very hard problem and one that isn't solved so far. And here would then be the extension of the weather data, the weather prediction data, where you have rather a temperature or humidity and a number of these kind of features represented as numerical values as representations for the prediction for the weather. And that would then be, I think, based on some kind of simulation. You're perfectly right. But the basic underlying problem that you want to solve is one that formulates your future prediction in terms of some numeric values, and that is the problem called regression that you should all have seen, I think. But there are other types of machine learning problems. Again, we're still on the problem side. So sometimes you want items and you want to return them. So web search is one of the classics here. So you want to learn which one is the most relevant, which one is the most interesting website that you want to return. So in some technical terms, they're all good websites. But now what is, from experience, for example, the one that people find most interesting? So it's not only the sort of classical information retrieval notions of PageRank or relevance, but sometimes you also want to learn from previous behavior, so that if people are more likely to click on a certain page, then it's a better result and it would be ranked up more. And that's all based on some previous behavior, also something that is learned, an additional component to the search algorithms. Something we sometimes see is when you add there is a sort of similarity search where you give a certain image and you want to find a similar one. Again, a similar problem. You want to I'm actually not sure why this is now here presented as a regression problem. So how Flickr does this big.
So you have to randomly calculate let's say the percentage of black and red, and then based on that they have to give you a ranking of which one is more similar to your photo.
Okay, it might be. I think it's a good guess. So the idea is that, or maybe you know. So the idea that came out of the class is that there are certain features that you can summarize an image in. So the amount of black and the amount of red and so forth, and predicting the amount of red and black that you want could be defined as a regression problem. But I don't really see where the learning comes in a way. But let's take that offline, and I will read it up again. Apologies. Another example of machine learning that we come across very often is that you don't learn from your own performance. So that was the example of that we had before, when you got a recommendation on the basis of the films that you've seen before. And then what would be a film that would have the same properties and so forth, the classification problem. But here what you want is to take other person's information, and based on some model that was trained on previous watching behavior of communities, you want to give a prediction. And of course we know that from Netflix and from Amazon that you watch a certain movie or a series and then they say, okay, other people who like that series, they also watch this. And this is a typical machine learning problem as well, a recommended system application on which this is based, that you get all those books in Amazon which tell you, okay, this is we recommend you this book because other people have actually liked this book and they have a similar interest in books than you have. And there was probably before your time of doing AI or computer science research, was actually a big competition that was also in the news, and that was the Netflix recommended system competition. So in the years 2006 to 2009, I believe, Netflix offered a prize of $1 million, I guess, to someone who was given a defined increase in the performance of their system. They had a recommended system, and that wasn't very good. And they had this competition for everybody who, and several research groups participated in order to develop a better algorithm to give better predictions. And I think in 2009 it was then won, and the people were awarded this prize. And that is, I think, one of the main assets also of Netflix, that they have this very strong recommendation algorithm that people aren't getting annoyed with. There is an interesting question related to this competition, namely that they wanted to start it again in 2010. They wanted a new round of this competition. And they had to stop it because there were lawsuits by Netflix users who thought this was an infringement of their data rights. And so before this case could be go to the courts, there was an agreement between the plaintiff and Netflix, and it was all stopped. But there was also never another competition. And I think it's an interesting question at the time, and it's still a very interesting question. What happens with our data? So how harmless is it? Is it okay that people look at my behavior and build some predictive models on it? Would it be still possible? I guess to the first question, it might be acceptable if these are generic models, but if it's possible to sort of derive my watching behavior out of this data, then this might become a different story already. So if someone could reconstruct what I've been watching out of this data that has been published, that is, then we might. Yeah, so I'm not sure I would like everybody here in the room to know what I watch on Netflix. And I think I have a relatively harmless Netflix behavior, but still I think this is something I would like to keep private. And if all this data, because this is individual data that was published, if that can be traced back to me, then we really have a problem. And maybe in Netflix behavior that is still acceptable, but if you go the step further and you go to predicting to publish data about health, then you're really very soon, very quickly in deep problematic fields and have to think about it very carefully. But again, we're going to go back to that on Wednesday. So now we've looked at classification, regression, collaborative filtering, and so we need one more, and that is an unsupervised algorithm, and that is clustering. And that basically is something that we get a group of similar things, set of data, where some things are more similar to each other than others, and we would like to recognize which of those belong together. So in the first instance, we would like to cluster them, and maybe in the second instance, we would even give them some names, these clusters. But this is usually something where we don't have a priori knowledge that a user says, okay, let's do those together, because if I would do that, then I would create a classification problem. But in many of those cases, so it's just some data that is given, and you want to assign some groups to it. And that's nowadays very often done with photos, for example. So I have some photos on Google Drive, and I get them nicely arranged according to some properties that they have. That's quite impressive, I think. So I don't say a priori, give me all the photos that have a church on it, but then you get a little album which gives you these kind of common properties. Yeah.
How is this different in classification? Because you basically just have class that bring those stuff together.
But I don't tell it before what class I wanted to have. It's the algorithm that determines itself that these two things are similar. And I don't tell it before, give me photos of a church. But still, I suddenly have photos that share the property that they have a large tower, I guess, or children playing, and then you have a different, they just put it in separate classes before anybody tells me them that those should be separate things.
So it doesn't apply a set of rules, just like in similarity.
That would be the method to derive it. But you could also do it by rules. So what I just said was a bit simplifying things. So if I would do it, I would say, okay, I look at the photos, and then if there is a child on it, then I would put it in one bucket. And if there is a tower, of course, a deep learning neural network doesn't do it that way. But in a way, the intuition remains that even a deep network tries to recognize some parts of a cat that sort of are similar. So two things and two photos have similar properties, and then they are clustered together. And I don't know whether anybody remembers these kind of websites from a long time ago, I believe. I don't know whether they're still in use. So Cluster, this was a website. You did web search, and you got your results back in a clustered way with tabs and a taxonomy of your results. So nowadays we have other things, we have info boxes, but I thought this was quite cool. So if you look for race, then you got your car, you got photos, you got games, you got definition, and so forth. And that was all based on automatic clustering and then labeling with some, I don't know which method they actually use for the labeling. So apparently it wasn't a solution that was necessary, or a problem that needed solving. So it hasn't gotten a place in search engines nowadays. But that was a very nice application of clustering. So you didn't tell it up front, I'm looking now for something ethnicity and race, but it did this split automatically. And that's what clustering is all about. So these were just some sort of intuitive example of where machine learning is used, but also that you can look and have to look at machine learning from different perspectives. And that is to understand the problem well, and that there are these 5 different problems. Also the matter of supervised and unsupervised is an important one. What is the information that I get from my user? What is the role of humans in this? And finally, also I think the notion of offline and online learning is an interesting one, that you have a machine that sort of the self-driving car has on the one hand a lot of machine learned models to make the decisions. And these models have been trained on simulations or controlled in a controlled way in cars before the car is actually driving, so in an offline mode, but then it would still apply some kind of online learning, and we would see that that's very similar to the behavior also if you apply machine learning in a game such as Go or Schnapsen, that you have these sort of online learning on the one hand and offline learning on the other hand. So these are important notions. Okay, so the second thing I want to do today is to get you into some machine learning methodology. So how do we actually do this? And want to start with the sort of how you have to set up your experiments and your research in the first place. And so this is sort of the golden rule of one of the golden rules of machine learning. It's sort of one of the deadly sins that you can make. The deadly mistakes in machine learning is if you do not have a proper testing set aside in your experiments. So what you have to do in machine learning is always split your data in some way into training data, maybe some held out data on which you can sort of validate your results, but then a testing data set which you not even look into before you put it aside for your final evaluation. Because as soon as you look into your testing data, you will overfit your model and your results are simply not valid anymore. So if you evaluate on some kind of data in your final project where you have already taken some peek into the testing data, your experiments are simply not valid. They are not correct. So what you usually do is you label your instances, and that is for regression or for classification, doesn't make a difference. You label the instances, for example, email, spam, or ham, and then you split them in a training set and a testing set. And you do that randomly, so no bias on it, but you really have to do that randomly. Often this is done 60-20-20, or in the next slide there is a better method explained, which is cross-validation, but you have to split it somehow. Your features are then some attribute value pairs or vectors that characterize your classes that you want to learn. And then you can do your experiments on your training data. You select a hypothesis, and then you compute, you tune, you optimize your model, your machine learning model, and then you complete in the end. Once you're done with this optimization, you calculate the results that you want to report on your testing set. So there's a better way, particularly if you have not that much data. It's a bit more expensive in terms of runtime, and that's called cross-validation. And that's basically that you pick a test set randomly of, in this case, 1 to the 5%, 20%, and you run your experiments. You train on the one set, and then you run your method on the test set, and then you pick another training set and another testing set without overlap, and you do that over the entire data set. And you do that, in this case, 5 times, but you can also do it 10 times, so it's called n cross n, what is it, n? I don't know. So it's n-fold, that was the word I was looking for. It's called n-fold cross-validation, so you choose how many of those rounds you will do, and then you have 1 to the n, 1 divided by n size is your test set, and you do it systematically that you see the entire set for testing and the remaining for training. And then you average over the results of your evaluation of the testing sets. And that gives you more reliable results, in particular if you have very few, if you have too little data. Because the big problem, of course, with machine learning, if you have not that much data, is that you can train a model on a certain amount of data, and this data is very biased, and then it won't work, or it will work too good on the testing set, and it won't be representative for unseen data. And for this, you do this cross-validation. Once you've done the sort of, when you're running your experiments, you report on the results that you get from testing it on the testing data set. And these are relevant notions. You basically, once you run your results, here in the classification case, in the binary classification case, here we have actually positive, so spam, or negative, so these are not spam. And then we have a prediction by our model. And if the model says it's spam and it is actually spam, then we call it the true positives. If the model says it's not spam, but it is spam actually, then this is called the false negatives. If we have predicted that it's actually spam, but it is not spam, then we have a false positive and the true negatives. And then if you want to calculate the quality of your algorithm, you just have to add up the numbers here. So all the true positives plus the true negatives give you all the quality on the correctly specified ones and the ones on the not correctly specified ones. And then there are many different notions for evaluating the quality of a learning algorithm. And that's accuracy, where you just take the true positive plus the true negatives normalized by the size of the negatives. And you take the recall, so these two are very important notions. You take the true positives and divide them by true positives plus true negatives. So these are, true positives plus false negatives. So these are those. So basically the true positives is the ratio of the ones that you correctly specified over all the ones that have the right property. So all the spam, how many of the spam did you find? So that's the precision. And the recall says is all the correct ones, so these true positives divided by the ones that you predicted correctly. Am I correct here? False positives, yeah. So
there should be brackets around that.
Yeah, these are in brackets. So these are, yeah. So of the ones that your system returns as spam, how many are correct? So these are very important notions that you really have to look into. Of course, when we do clustering, then this is more difficult because we don't have those notion of true positives and true negatives, because we actually don't have this side. We don't have this action. We don't know actually whether something is spam or whether it is a church or a bee or whatever. So in this problem, if we address the problem of clustering, then we look more into how big is the inter-class similarity. So we look into, is the similarity between the individual objects within a cluster higher than with the outside of some other elements of some other cluster. And then we also have some extra tasks that we can, so end-to-end tasks as they are called. So how good is my clustering in an application? But usually evaluating a clustering algorithm is far more difficult than classification or regression, because you don't really know what the right answers would be. Yeah, I believe that this is now on the evaluation side. So really look through this pipeline of how do you set up a good experiments in machine learning, and then how can you evaluate, how can you actually say that your algorithm is good or not. So these were the two things we've seen now. And now the next thing is the recipe for building a machine learning algorithm. But we do that starting at 2:30, please.